Look at the sheer power output of an elite track cyclist inside a velodrome. At maximum exertion, the human body burns through fuel and fluids at a rate that pushes cellular biology to its absolute breaking point. For decades, sports nutrition relied on static daily targets. However, those fixed benchmarks fail to account for the acute energy demands and metabolic shifts required during specific training blocks. The current scientific standard is nutritional periodization. This is the calculated manipulation of specific substrates, the underlying metabolic fuel sources like glucose and lipids, to intentionally force cellular adaptation. This schematic visualizes physiological homeostasis as a balanced equation. When we introduce severe stressors like exertional heat stress, voluntary dehydration, or glycogen depletion, that balance shatters. Dietitians don't maintain steady-state balance. They actively manipulate these variables, engineering precise deficits and surpluses to trigger physical upgrades. Our analysis relies on three distinct pillars. The first is proactive substrate manipulation through specific protocols like SLTL. The Sleep Low, Train Low, or SLTL protocol, is a nutritional strategy that purposefully restricts carbohydrate intake before and after training sessions. The second pillar requires managing unavoidable time-restricted deficits, such as those occurring during Ramadan. The third pillar involves defending plasma volume against severe, catastrophic fluid shifts. Peak athletic optimization requires the precise periodization of substrates and fluids. Coaches must deliberately impose physiological constraints to force adaptation, or engineer specific internal defenses to survive environmental failure. At the microscopic level, altering circulating fuel sources triggers a transition in cellular fuel preference, shifting the primary pathway for energy production. This two-panel diagram compares fuel availability. Panel A shows a standard pre-fueled training session with high baseline glycogen. Panel B visualizes the proactive deficit of the SLTL protocol, requiring a sharp drop in carbohydrate intake immediately following an evening training block. The SLTL protocol intentionally starves the athlete of carbohydrates overnight. This forces the body to execute the next morning's training session in a completely fasted, glycogen-depleted state. Plotting the physiological response onto this timeline reveals an inverse relationship. As glucose availability flatlines, the resulting metabolic stress forces the fat oxidation curve to spike dramatically during the morning exertion. Practitioners also micromanage baseline glucose prior to exertion using strict glycemic index metrics. For example, they test feeding an athlete 1.3 grams of carbohydrate per kilogram, specifically comparing a low glycemic meal at GI 47 versus a high glycemic meal at GI 80. Once the prescribed deficit has forced the required cellular adaptation, the focus shifts entirely to accelerating post-session recovery using novel ergogenic combinations. One precise recovery protocol involves ingesting exactly 1.2 grams per kilogram of body mass per hour of carbohydrates, stacked with 25 grams of ketone monoesters, or KME. KME is a highly concentrated exogenous ketone supplement used to rapidly elevate circulating ketone levels in the blood. This specific KME and carbohydrate combination accelerates the restoration of intramuscular glycogen and shifts the systemic metabolic profile toward faster recovery when compared directly to standard isoenergetic dextrose placebos. By proactively forcing the body to train in a low substrate state through SLTL, and then immediately rescuing the system with hyper-precise KME protocols, coaches maximize deep cellular adaptation without crushing the athlete's long-term output. Beyond programmed interventions, athletes must navigate unavoidable environmental and cultural constraints. The most severe example of time-restricted feeding is Ramadan. This 24-hour metabolic clock maps the rigid constraints of RIF. Ramadan intermittent fasting, or RIF, is a religious dietary practice involving complete abstinence from food and water from dawn to sunset. RIF inflicts a significant systemic impact. Athletes experience an average daily energy drop of 293.8 kilocalories, running concurrently with measurable reductions in absolute carbohydrate, lipid, and water intake. To preserve performance, training blocks are meticulously shifted. Moving a session to a fed state immediately post-iftar yields significantly higher energy availability compared to training in a severely depleted fasted state right before the fast is broken. Dietitians employ nutritional triage by manipulating the suhoor pre-dawn meal. They contrast an early intake versus a late intake timing to artificially drag substrate availability deeper into the daylight fasting hours. We must contrast this tightly managed acute caloric deficit with the chronic pathological condition known as RED-S. Relative energy deficiency in sport, or RED-S, is a physiological syndrome caused by an athlete's caloric intake falling short of their daily expenditure. The clinical protocol required to reverse RED-S mandates a sustained, aggressive daily energy surplus, increasing intake by exactly 200 to 400 kilocalories per day. This targeted caloric surplus is strictly engineered to normalize REE and eliminate LEA. Resting energy expenditure, or REE, is the baseline number of calories the body burns while at complete rest. Low energy availability, or LEA, occurs when the body lacks sufficient leftover energy to support basic physiological functions after exercise. Whether navigating the strict boundaries of cultural fasting or rescuing a metabolic crash in RED-S, precise timing and caloric adjustments dictate baseline metabolism survival. Transitioning from energy deficits to catastrophic fluid deficits, we look at the extreme rapid weight loss strategies utilized in combat sports. Acute voluntary dehydration disrupts the established osmotic pressure between intracellular and extracellular compartments. Practitioners track these fluid shifts using BIA. Bioelectrical impedance analysis, or BIA, is a clinical method that measures body composition by passing a weak electrical current through tissue. This graphical readout displays a BIA simulation. Rapid hydration reductions cause distinct, measurable spikes in the 20 kHz and 100 kHz impedance indices, reflecting an acute dehydration state. Voluntary dehydration is a controlled choice. Involuntary fluid loss under extreme environmental conditions leads to EHS. Exertional heat stress, or EHS, is a critical elevation of core body temperature caused by intense physical activity in high-temperature environments. Under exertional heat stress, standard water ingestion fails to prevent hypohydration. Lacking osmotic gradients, plain water passes straight through the system without being retained. To counter this, practitioners introduce hyperhydration agents, specifically sodium and glycerol. These act as mechanical osmotic anchors, forcing plasma volume expansion prior to the exercise. This diagram of fluid compartments illustrates the deployment of the HAMS protocol. High amylose maize starch, or HAMS, is a fermentable resistant carbohydrate that acts as a powerful osmotic agent to actively engineer fluid retention. The exact preloading intervention requires administering a beverage containing 12.7 grams of fermentable resistant starch exactly 12 hours prior to EHS exposure. The fluid compartments swell to a hyperhydrated state. The post-stress recovery protocol demands an additional 6.2 grams of resistant starch. This specific osmotic anchor is required to successfully replace 150% of the incurred fluid deficit. By weaponizing specific osmotic agents like HAMS and glycerol, high-performance dietitians preload a human's fluid compartments, allowing the athlete to survive heat stress that would normally cause systemic hemodynamic failure. This dashboard maps an athlete's entire macro cycle. When we view a high-stakes training block through the lens of modern dietetics, we see a layered matrix. First, we layer in the programmed physiological stress of the SLTL glycogen manipulation curve. Second, we overlay the precise temporal feeding windows required to survive the constraints of Ramadan fasting without losing muscle mass. Finally, we map the preloading of osmotic hyperhydration agents immediately ahead of the culminating exertional heat stress event, starving the muscle, racing the clock, and flooding the plasma. These vastly different approaches form a unified, highly controlled physiological matrix. Ad libitum intake, eating or drinking as one feels like it, cannot match the precision required to maintain plasma volume or optimize glycogen levels under extreme stress. High-performance dietetics is a calculated mathematical discipline. True optimization is a dynamic engineering problem, requiring constant adjustment based on exact environmental and exertional demands. Championship-level athletic performance demands the ruthless, precise periodization of physiological deficits and surpluses to dictate human adaptation.